Welcome everybody to Viking.TV, to another Expeditions live stream. I'm delighted to say that today we have two world experts with us to discuss the wonderful subject of icebergs, and we'll get into that in a moment. A little bit about expedition content. This is in order to provide some insight into the experiences of participating on a Viking expedition. And as we're preparing to go to sea, we also have fantastic opportunity to work with very accomplished colleagues. If we look familiar, you will see that one of our guests is Professor Julian Dowdeswell, and I'll be introducing more thoroughly in a moment. And he has previously made 3 Viking.TV presentations that were broadcast in the summer around the Scott Polar Research Institute, around the subject of Antarctica and of the Arctic. So I recommend to go and see those if you would like to explore more about those subjects. If you think I'm familiar, then I've also made a presentation with a colleague of mine, Jørn Henriksen, about reflecting on expeditions in the past. By introduction, my name is Damon Stanwell-Smith. I'm the Head of Science and Sustainability at Viking Expeditions. By brief background, I'm a marine scientist with an academic background with the British Antarctic Survey, and I now have the privilege of working to bring the research, scientific research component of Viking Expeditions to fruition. And now I'm going to introduce our guests. May I first introduce Professor Olav Orheim. Olav is a glaciologist and climatologist who has led more than 20 scientific expeditions to the Arctic and Antarctica. He worked for 40 years at the Norwegian Polar Institute, including 12 years as managing director, and at the same time, he has been the professor of glaciology at the University of Bergen. Olav set up the Troll Station in Antarctica, which is Norway's permanent research station. He's also the founder of the Norwegian Glacier Museum in Fjellland and the Polaria Centre in Tromsø. Olav has been the member of the executive boards of most of the organisations devoted to the study and protection of the polar regions, including the International Arctic Science Committee and the Scientific Committee for Antarctic Research. For many years, he was the vice president of the International Glaciological Society and the chair of the working group on glaciology of Skarv. He's currently a member of several international boards and committees and the president of the Fram Museum in Oslo. In 2007, he was made a Knight of the Royal Norwegian Order of St. Olaf, and in 2012, a Knight of the Order de Saint-Charles of Monaco. So, Olav, welcome.
Thank you.
And our second guest is Professor Julian Dowdeswell, who is a British glaciologist of Cambridge University's Scott Polar Research Institute, where he has been the director for the past 19 years. He studies the form and flow of glaciers and ice caps and their response to climate change, and the links between former ice sheets and the marine geological record. He's worked on the ice and from aircraft in Antarctica and in many parts of the Arctic. He's undertaken many periods of work on icebreaking research vessels in the Southern Ocean and the Arctic. He's also represented the UK on the councils of both the Scientific Committee on Antarctic Research and the International Arctic Scientific Committee, and is a past chair of the UK National Committee on Antarctic Research. Julian was awarded the Polar Medal by Her Majesty the Queen and has also received the Founders Gold Medal from the Royal Geographical Society. And he's recently written co-written a popular science book called The Continent of Antarctica. And may I just add one other point, is that Professor Dowdeswell is the chair of Viking Expeditions Scientific Advisory Group, which more will follow on future episodes of Viking.TV. So welcome, Julian.
Thank you, Damon.
So as you'll see, we have two fantastic world authorities on icebergs with us. I'm looking forward to the conversation. The form we'll take is we're going to go through a number of themes over the next hour, and we're going to start by introducing icebergs. We'll start from the fundamentals. And this broadcast has been inspired by recent global news that came out last month about the possible risks of currently the world's biggest iceberg, indeed one of the biggest icebergs, I understand, ever on record, known as A68A, and its movement across the Southern Ocean heading towards the UK overseas territory of South Georgia in the Southern Ocean. Now, we're going to get to the specifics about A68A later in our discussion. However, I'm going to start by asking a very simple question. What is an iceberg?
Yeah, if I just kick off on that one, Damon, there are two kinds of ice that you can see from a ship as you travel towards Antarctica. The first are large icebergs. These are large chunks of ice which are made up of fresh water, and they originate from the breaking off of ice from the margins of ice caps and ice sheets that reach the sea. Those ice caps and ice sheets, of course, are formed initially from precipitation, which falls on the Earth's surface and builds up and densifies year on year into glacier ice. So the origin is in densified snow. And when ice reaches the sea, chunks of various sizes, from the size of something like A68, which is the size of Delaware, or that sort of magnitude, and about 150 kilometers, just over 100 miles in length, to small little chunks that we sometimes call bergy bits if they're less than 10 meters across. So all of those large chunks of ice that break off or carve, as we call it, from the edge of the ice sheet, are of fresh water. Now, 9/10 of that iceberg is below the sea surface because, of course, there are air particles trapped as bubbles within the ice. So 9/10 of the ice is below the water surface, and only a tenth or a ninth, perhaps, dependent on the density distribution and the precise shape of the iceberg, is above the sea surface. Now, we can contrast that with the other floating ice in the sea, which is called sea ice. And sea ice is simply the frozen sea surface. And as different from icebergs, which can be hundreds of meters in thickness, sea ice is usually just a couple of meters in thickness. The thickest sea ice, the thickest undeformed sea ice, is just 3 or 4 meters in thickness. It can become thicker if it sits in the ocean for several years and freezing at the base takes place. It can also become thicker if the ice actually is pushed together and ridges under wind and ocean current pressures. But in general, sea ice is just a thin cover that waxes and wanes across the Arctic and Antarctic seas, building up during the winter and melting to some extent during summer. So fundamentally, the sea ice is salty, not as salty as the water from which it freezes from, because some salts are rejected during the freezing process. But sea ice, to summarise, is simply the frozen sea surface, whereas icebergs are derived from the breaking off of chunks of ice of huge size sometimes from the parent ice sheet.
Julian, thank you very much for the description of the two ways in which icebergs can form. I see now here an image of an ice shelf. Please do share what's going on here.
Yeah, so we've got a few photographs here, and the first one shows the South African research vessel, Glaciologist 2. I've actually taken this photograph from an aircraft. We're just coming into land a few miles from the ice shelf front, and you can probably just make out in the photograph a little encampment near the front of the ice shelf. And what we see here then is the floating margin of the Antarctic ice sheet. So the ice that you see here is a floating ice shelf. It's actually about 300 meters thick, and we can just see the upper 30 or so meters of it above sea level. But below it's about 300 meters thick, and there are a number of hundred meters, a number of hundreds of feet of water underneath that floating ice shelf. But if we were to go into that cavity a few tens, or in some cases a few hundred kilometers from the margin, we would actually find that ice is fed from the interior of the Antarctic ice sheet. So the reason it flows at the velocity it does, and the reason in part it's the thickness that it is because it's fed from the interior of the Antarctic ice sheet. And what we can see in the next image is a close-up of the ice shelf itself. And here the ship is butting up right against the ice shelf when we're transporting people between the ice shelf surface and the vessel by what in British parlance we call a whirlgeordie. It's a little basket, and you hold on to the outside of it, and we're being lowered from the ice shelf by a crane onto the deck of the ship. But what you can see if you look at that 30 metre or so ice shelf margin that's above the sea surface is you can see a number of horizontal layers in it. And that represents the layer cake structure of both the interior of the Antarctic ice sheet and of the ice shelf, which is fed from the interior. And those layers represent year-on-year accumulation of ice on the surface of the ice sheet. If we go to the next image, we can see what happens when the edge of the ice shelf carves off a series of icebergs. And these are icebergs actually in the eastern side of the Ross Sea, on the other side of Antarctica from the Weddell Sea. And these are in various stages of melting. One or two of them may have overturned. And the reason they're not completely tabular or table-like, as we saw from the first image from the aircraft of the ice shelf, is because they've undergone some degradation and perhaps fragmentation since they were first carved. And around the periphery of the Antarctic ice sheet, you can see thousands of these bergs. If we go to the next slide, we can see, by contrast, the margin of an Arctic outlet glacier of the Greenland ice sheet. And here, again, from a vessel pushing through the sea ice towards the edge of the ice sheet, we can see cliffs. In this case, probably about 25 meters high. But in this case, and this is true of most of the Arctic as compared with the Antarctic, here the ice is not floating at its margin, but it's actually grounded on the sea floor. And when ice is grounded on the sea floor, it tends to produce large numbers of small and irregular shaped icebergs, as opposed to the big floating ice shelves, which produce small numbers of very, very large icebergs. So there's a strong contrast, and we can see this again in the next slide, between the Arctic and the Antarctic. Here again, we're looking at an Arctic glacier draining an ice field in Greenland. We can see the cliffs, we can see debris on the surface, which is derived from the mountainous interior of Greenland. But again, large numbers of small irregular icebergs will be carved from grounded ice, whereas floating ice produces large numbers of small numbers of large tabular icebergs. So there's a strong contrast there between the floating ice of Antarctica and the generally grounded ice, apart from a few ice tongues in Greenland fjords. So therefore, in general, the Greenland ice sheet produces large numbers of smaller bergs and just a few large tabular icebergs where there are limited amounts of floating ice. But it's the Antarctic ice sheet that produces the majority of the large tabular icebergs. And if we look finally at the next slide, this is just a nice little visual demonstration of the vast underwater area that is the underwater volume that is difficult to see. We can see the surface of the iceberg here, and we can see through the blueness of the water lurking beneath the waves, the great expanse, the 9/10 or 8/10, depending on the shape of the ice mass, of the underwater keel, the submarine keel of the iceberg.
Fantastic.
That picture actually has a nice little bit of information on it that's been tilted, that iceberg. So you can see that a little bit earlier, that iceberg has been more horizontal, and now you see parts of it exposed, which has been underneath the waterline. And often when we see icebergs in the Antarctic, they have been slightly tilted, and you can see the old waterline as coming across, because right at the waterline, there's much more erosion of the iceberg because of wave undercutting, etc. So when it's in the open water, it always gets most eroded around the waterline.
Fantastic. And indeed, I imagine both of you, if there's one question that you're probably asked is, why are icebergs mostly underwater? Right, that's the question that I often get asked. And I understand that not all ice in the sea are icebergs. May we now reflect on the difference between icebergs and other ice in the sea?
Yeah, we could go on to the next picture here, which shows nicely the South African research vessel that I was on a couple of years ago, moving through the sea ice of the Weddell Sea. If you look carefully, right on the horizon, you can see a couple of large tabular icebergs. But basically, we've got what is called pack ice here, and this is the frozen sea surface. You can see the freeboard, the above water part of the sea ice, is only a number of centimeters or about a foot in height, which indicates that the sea ice here is very thin. It's less than a meter, less than 3 feet in thickness. This is what we call open pack. When the wind and ocean currents push the ice together, we would have closed pack and you wouldn't see the open water areas that you see here. One of the reasons that sea ice is particularly important in terms of its impacts on climate change is that when the sea freezes and the sea ice actually forms, the sea ice is not as salty as the water from which it comes. And therefore, those rejected salts mean that the water as the sea ice forms is both very cold and very dense. And in fact, it's about the densest water anywhere in the global oceans. And that water sinks, therefore, because of its density, to the seafloor. And in the Arctic, it flows northwards as a great big conveyor belt close to the seafloor. In the Arctic, it flows south at depth after it's been produced by sea ice formation in the Norwegian Greenland Sea and the Labrador Sea. And the return flow that we see in the Northern Hemisphere, the return flow, the upper 1,000 meters, the upper 3,000 feet of the ocean, which flows north past Britain, past Norway and past Spitsbergen, makes those three areas the warmest place for their latitude anywhere on the globe. But the driver of that circulation, and one of the major drivers of the general circulation of the oceans, is actually the production of that dense water through sea ice formation. So sea ice formation is not just something that we see in the polar regions, it's something whose effects ramify through the whole vigor of the global circulation system, which we call the thermohaline, or ice and temperature and salt-driven circulation of the global oceans. So changes in sea ice actually affect the global circulation of the whole ocean system, and therefore affect the whole of humankind.
It's a big subject.
Yes.
Thank you for the explanation. I'm conscious also that you mentioned pack ice, and maybe there's the next image, James, that you could, if you could show, that we know in popular culture that Inuit have hundreds of names for snow because they live in it. I wonder, Olav, whether as a Norwegian that the many names for ice may also resonate with you, because we've briefly touched on pack ice, but I am conscious that there are many more names for ice, sea ice, than simply icebergs and pack ice.
Well, let me make a couple of points. First of all, you briefly mentioned that these things are, most of the, whatever it is, sea ice or glacier ice, icebergs, most of it is beneath the water surface. And that's just like the ice you have in your drink if you put ice cubes in your drink. There's nothing strange about this. It's just the density is just a little bit less than the water, so it floats. And most of it is still below the surface. And sea ice and icebergs is just the same way, it's ice. Now, some of these icebergs that we see in the Antarctic, the tabular ones, have much more snow at the upper surface, so they float a bit higher than just 1/10. But there's still, most of it is under the water. In terms of names, I'm not quite sure that there are hundreds of names in Inuit language. What the Inuits do when they talk about snow is they put together several words. So whereas we have if you say, we would say it's wet snow, and it's 2 words. In the Inuit, it becomes 1 word, and that word is different from dry snow. But actually, it's not a way of making words that means that there's 100 different words. But there are, both in Inuit language and in Norwegian language, yes, there are words which you will not find in English, which are words of snow. So we do have more words. And if you talk to a reindeer herder, for example, up in Arctic Norway, they have words for snow that we don't have in southern Norway, because the reindeers herding, for them it's very important if the reindeers can get through the crust to get to the food beneath. And so they have words related to how easy the reindeer can eat, which we don't have when we go skiing. We don't worry about whether we can eat the moss underneath or whatever the lichens. Yeah. So there are differences, but it's not 100 to 1. It's not
yes.
No. Yeah. But that was just a minor point.
Well, it's good to be corrected.
Yeah. We can have a look at the next couple of slides and see a couple of different sea ice types in those. So this picture actually shows, first of all, what we call first-year sea ice. It's quite thin. Each of those flows, which have been broken up probably by the action of wind and swell waves, is a few hundred meters across. So these are large ice flows. And the flow, when we call an ice flow, it's FLOE. So it is an ice flow. And you can see a series of these are quite geometrically similar ice flows, and a single iceberg in the middle of them. And you can see that the iceberg is holding some debris. And then if we go to the next slide, we can actually see the sea surface freezing. This is near Captain Scott's and Shackleton's huts in the McMurdo Sound area of Antarctica. And in fact, the big American base at McMurdo Sound is just beyond the coastline, the hills that you see in the distance in the main slide. And what you can see is the sea surface has just started to freeze here. We're here right at the beginning of autumn, the Antarctic autumn, and the sea simply freezes. And the initial stage of freezing is called grease ice, and the sea surface just has a grey sheen on it, and you can see that in the main image. It's grey, and you can actually see the swell rolling through an effectively flat surface, which is just beginning to freeze. And if we look at that surface in detail, the main image has the grease ice with small pancakes, and then the detail is what we saw just about an hour later, when the grease ice has turned almost entirely into these little pancakes, each one about a foot across, something like that. And you can see that as they bob together in the sea, they push up little moats around, little barriers around them, to make the edge of each flow be picked out really easily in the low light conditions. And then eventually these individual pancakes will freeze together into solid sheets of sea ice. So that, if you like, is the beginning of the formation of sea ice as the sea cools in autumn.
I love the food description, as Olav mentioned, about snow that reindeers can eat through. You've got pancakes there, which maybe not something necessarily that you have on a polar ship.
Sounds a bit like my cooking. Grease ice turns into
exactly. And also reflecting on actually the name iceberg, I understand that you have the lumps of ice in the water have to be of a certain size to be considered an iceberg. I personally have always loved the rather onomatopoeic name of a growler, or indeed bergy bits. I wonder if either of you had any reflections on the naming of ice and how it interacts with ships.
Well, a growler is less than 5 meters above the surface, usually less than 10 meters across, if you like. They're small bits of icebergs, but you should realize that even that size if you run at it at full speed with any normal type of ship, unless the strongest of the icebreakers, it will actually dent the bow and possibly even sink it. The icebergs in the Antarctic are much bigger, and in that sense, actually are much safer, because you see them on the radar. You will big ones, of course, you can see most of the time. You see them visually, but the ships going to the Antarctic there are sections of the open Southern Ocean where they're more worried about growlers, because if they're there during the night, which you will be, of course, if you're not right there in the middle of the summer, you actually cannot see the small growlers, and you are worried about them. And of course, that's what Titanic was not that huge an iceberg. If it had been a big one, they probably would never have run on it either, except they didn't have radars, of course, in those days. So that's another part of the story.
Absolutely.
Yeah. Growlers is not really so exciting, because most of the time we don't see them. They're right at this water surface. It's the nice big white ones that we like to look at.
Yes. You hear the growlers bouncing along the side of the hull.
Yes.
And so if a iceberg has to be a minimum of 5 meters or whatever, 16 feet above the water, is the next scale is a growler. And how about bergy bits and others? Are there other? Is it more just descriptive, or are there specific ways in which they're classified?
Bergy bits is just descriptive, but there are classifications of the shape of icebergs. There's no formal agreed on way of doing it, but there are people you can talk about them in terms of the shape being dome shaped, being having very often they have a hollowed out part in the middle, like if it could be a dock that you could put a ship into. And then expressions for all of these. So you have pinnacle icebergs, etc. But the big difference which we talk about in the Antarctic are either they're tabular or they're not. And most of those that are not have actually been tabular once upon a time, been broken up into smaller pieces and then eventually overturned. And that's how they stop being tabular. But the tabular ones have never overturned. They've been floating in that way all the time and just drifting around. And some of them drift around for many, many years, like this famous A68 and many others, where I have records of icebergs drifting around Antarctica for at least 14, 15, maybe 20 years. Yes.
And we could also point out that, of course, a lot of these big tabular icebergs, dependent from the particular ice shelf that they carve or break off from, can be hundreds of meters, up to 1,000 feet in thickness. And therefore, in shallow water, they do actually ground in some places on the sea floor and actually plough up the sea floor. And their keels, as we can see in the next image, produce all sorts of delicate and somewhat chaotic patterns on the sea floor. And you can see here a series of bergs ploughing, in this case, the sea floor on the east side of the Svalbard archipelago in about 50 meters, about 150 feet of water, something like that. And you can see the individual tracks of the bergs, and one of them indeed has formed a loop, probably over a period of a single tidal cycle of about 12 hours. And you can see if you follow the loop around, you can see that it's even cut its own track and then actually become disengaged with the seafloor. So quite often the seafloor up to about 400, 450 meters of water depth around Antarctica is very, very heavily ploughed by the action of deep-keeled icebergs. And that actually acts in one way to renew and renew the sediments, and to mean that the development of the biota, the organisms that develop on the seafloor in the Arctic and the Antarctic, is actually disturbed. It's a bit like the effect of falling trees in the tropical rainforest. Falling trees renew the biota, and in the same way, iceberg keels do that in the Arctic and Antarctic seas. I've worked quite a lot with multi-beam echo sounding imagery of the sea floor, and that gives a digital elevation model, a picture of the sea floor in plan. And if we look at the next image, we can see a whole series of different types of iceberg plough mark. The image on the top left is the one that we saw originally. The one on the top right, we actually named the skier, because it looks to us like somebody actually skiing with two skis downhill. And you can see a lot of different patterns. The bullseye on the mid left shows an iceberg that is probably moving up and down with the tide to produce a pit. And the one at the bottom left, a sort of corkscrew, that is where the berg is in general drifting in one direction, but its course is elliptical because of tidal motion. And then we can also see the layer cake structure of the seafloor and subsea floor on the bottom right. And there one can actually see the iceberg looking into the underlying sediments of the seafloor. And these plough marks of the biggest tabular icebergs can be miles across, and they can be tens of feet in depth. So these are big features on the seafloor, but below about 500 meters of water depth, you don't find them, because the maximum keels of icebergs carved from the Antarctic ice sheet and from the fast-flowing outlets of the Greenland ice sheet are seldom more than 500, 550 meters in thickness.
And there's two things I'd like to just ask. Is you mentioned multi-beam. I understand that's multi-beam sonar, so it's using sound to image underwater. And those images, I'm guessing that the seabed isn't green and orange and red.
No, that's right. No,
that's colour that is added to add extra information.
Exactly right. Yes. Imagine in a ship, in a boat on a lake or a ship out at sea, you would normally have a single beam echo sounder, where the echo sounder sends out a pulse of sound energy. That pulse goes down and is reflected back from the sea floor to the receiver on the parent vessel. And because we know the speed at which sound goes through the water, we have to divide by 2 because the sound went down and back up. We convert to distance, and that's how a simple echo sounder works. A multi-beam echo sounder is one where a whole series, a fan-shaped series of beams, is sent out from the parent vessel, from a series of geometrically arranged transducers on the hull. But the method is exactly the same. You measure how long it takes to get there, how long it takes to get back from the seafloor, but it gives you a whole set of point measurements of the seafloor. And of course, the third dimension is added by the ship moving forward all the time. So, like, pulse of energy, ship moves forward, pulse of energy, ship moves forward. And in that way, you build up what we call a digital elevation model of the seafloor, which provides you with the regional bathymetry, the regional water depth of the seafloor. And we take these into computers and we digitally enhance those, as you say, Damon, to provide the false colour images that you see there.
Thank you for the explanation. And for viewers that are planning to come on Viking expedition ships, we have fitted on one of our vessels, a survey vessel, which is within the ship, on one of the ribs, a Norwegian Kongsberg multi-beam sonar. So to undertake the kind of imaging and research that Julian is highlighting in those images as well. So something to look forward to for those that are planning to join us on Viking expeditions.
Yeah, just to take that on a stage further, Damon, the sea floor in the polar regions and in other parts of the world contains a huge amount of information about the geological history of the Earth. And in the polar regions, where the ice has retreated from its full glacial position 18 or 20,000 years ago at the edge of the polar continental shelves, there is a whole palimpsest of different kinds of seafloor landforms which were produced when the glaciers were there and as the glaciers were retreating. And we can actually use that palimpsest of submarine landforms to reconstruct the form and flow of past ice sheets. So it's quite the multi-beam echo sounder and the ancillary stratigraphic tools that we use are actually giving us a really good window on the reconstruction of glacial history.
I imagine it's like studying the moon and understanding history through looking at the impacts.
Well, do you know what? It's an interesting analogy, but in fact, the imagery that we have of the moon, or indeed of somewhere like the surface of Venus or Mars, is much more complete than we have of the seafloor of the Earth, simply because we've got an ocean in the way, and it's harder to actually collect the imagery. And indeed, it might also be interesting to point out that probably the least accessible places on planet Earth are the water-filled cavities beneath the floating ice shelves that fringe Antarctica that I talked about earlier on. And those are very, very hard and dangerous to get into, and no human has ever been into those places. A few remotely operated vehicles have made a few forays underneath the floating ice shelves, but those are almost unarguably, I think, the least explored places on planet Earth.
I look forward to it. I'd like to highlight a point Olav made about the typology. I imagine, Olav, you're quite well placed to discuss the typology of icebergs. And as Julian has highlighted, they scour and thinking about how they move. I understand that, of course, tracking icebergs and cataloguing icebergs and having a greater understanding of icebergs in the round is an important part of understanding the damage, or indeed the interaction that the icebergs have with the seafloor. Would you like to care to elaborate on how all of that is done?
Well, there are many ways, of course, of tracking icebergs. Today, all the big icebergs get tracked by satellites, and there's a catalogue of the icebergs and both of the past and the new ones coming out. And of course, the very, very biggest ones generate public interest as well. But about 40 years ago, before satellites were as we might say efficient as today, and before we could look through clouds with satellites the way we do today, we actually started also making iceberg statistics, and all the Antarctic nations joined together to equip their ships with something we call the blue forms, where icebergs were recorded. And before that, we only had observations of a few icebergs by chance from some ships. Once we got a systematic collection, we discovered there's at any time more than 100,000 icebergs floating in the Southern Ocean around Antarctica. There's a lot of them. And there are, of course, variations from area to area. Coming out of the Weddell Sea is actually the biggest stream of icebergs that come out along the Antarctic Peninsula and then out into the South Atlantic Ocean. Because by chance, that sort of is like, there's a anti-clockwise current going around Antarctica, and then it brings out along the peninsula and then out into the clockwise current called the circumantarctic current. But there are big differences in density of icebergs around Antarctica. Surprisingly, there are very few in the Ross Sea, for example, where the carving of icebergs tend to be very large icebergs, very seldom are carved, whereas other areas, like along the Antarctic Peninsula on both sides, there's a large number of carvings, very high density of icebergs, but much smaller than the biggest tabular ones that we see coming out of Ross Sea. So the big variations, but it's interesting for us because we can put this then into a picture of trying to discover how much is breaking off from Antarctica, and into the much bigger question, namely, is the Antarctic ice sheet stable? Is it losing mass? Because the icebergs themselves float and don't affect sea level. But if the Antarctic ice sheet was to lose mass, then of course we would see an increasing sea level. And that is one of the big issues now being discussed, how much mass is being lost from the Antarctic ice sheet. I think nearly all glaciologists today agree that there is a net mass loss from Antarctica, meaning there is a sea level rise, perhaps not a very huge one yet, but in the long run, that is perhaps the biggest question mark in future sea level rise, is what will happen with the Antarctic ice sheet. And to finish off, why is it, what's happening? Well, perhaps one of the biggest effects now is the fact that the ocean surrounding Antarctica is getting warmer, and that the warmer waters are coming underneath the ice shelves, which is then melting these from the underside, and that's speeding up the flow from the Antarctic ice sheet out into the ocean. Is becoming faster in some areas, simply because the restraining force of the ice shelf is becoming less, putting it in simple terms. And it's a very, very interesting science in this, and there's going to be science in this area for the next 20 or 50 years, I think. So there's a lot to do for the glaciologists coming after Julian and myself. Yes.
Understanding ice. Oh, sorry, Julian, go again.
Well, Olaf, very, very interesting point. If I just elaborate on the contributors to sea level rise at the moment, the main contributors to sea level rise today are firstly the warming of the global oceans. The oceans are warming, and therefore the volume of the oceans expands. You could do the same experiment at home with a glass of water, warm it, but it'd take up more space in your glass. But the glaciological, the ice on land that's being effectively transferred back into the ocean is largely at the moment from the small glaciers and ice caps in the mountains of the world and in the Arctic. The Greenland ice sheet is also a very significant contributor to global sea level. And as Olaf quite rightly says, the Antarctic is likely to overtake those in due course as, in the end, the most important contributor to global sea level rise. But it's not the most important at the moment, and you can see it's effectively slightly insulated from the rest of the global climate system by the circumantarctic current. It's difficult to get warmer air masses to the Antarctic, and Olaf quite rightly points out that warmer waters have started to come into some sectors of Antarctica and started to melt the Antarctic ice sheet from below.
And in fact, picking up on a point Olaf made about the Weddell Sea, which for viewers that are looking at a map, is on the east side of the Antarctic Peninsula. The current, the gyre that comes and brings icebergs out the Weddell Sea, I think maybe is a nice segue to discussing A68. So for watchers that have maybe had been sensitized to the ideas of what a really huge iceberg can be, those global news items that came out early November, so about a month ago now, certainly have got people thinking. And Julian, I understand that the Scott Point Research Institute and others ran an expedition to the Weddell Sea last year.
Yeah. During the time we were aboard the South African research vessel Gullis 2, we were aiming to work on the floating ice shelves on the east side of the Antarctic Peninsula, in particular an ice shelf called the Larsen C ice shelf. But as we made our plans to go there in January 2019, the calving in July 2017 of the huge iceberg A68 from the Larsen C ice shelf meant that we had difficulties of access to that whole area. A68 is about 130 kilometres, just a bit less than 100 miles in length. It's got an area of about 4,500 square kilometres. It's about the size of the state of Delaware in the USA. And when it was carved, it was about very roughly 300 or so metres in thickness. So this is a huge block of ice that is actually coming north from its calving in July 2017 as we're trying to get into the same area about a year and a half later. And if we look at the next slide, we can actually see iceberg A68. I think we're probably the only ship ever to have touched A68. And you can see the iceberg on the left of the image. It's sea ice in the foreground, and you can see right into the distant horizon the edge of that iceberg with cliffs about 20-25 meters in height, something like that. And one of the things I thought when we first saw iceberg A68 is how easy it was for the early explorers to actually mistake a great ice wall like that for being land or an ice-covered island rather than something that's in motion. And it showed me a lot of respect for the early mappers of both the Arctic and the Antarctic, because they had to distinguish between these huge tabular icebergs and what was really in the long term ice just sitting on land. And if we look at the next,
can I actually, Julian, just to point just there is I'm reflecting on the name Larsen Ice Shelf. I believe it was named after Carl Larsen, the Norwegian whaler.
Yes, Carl Anton Larsen.
H.C. Larsen. H.C. Larsen. That's right. H.C. Larsen, indeed. And H.C. Larsen, in his vessel, the Jason, in a very light year for sea ice, when there was a lot of open water down there, just at the end of the 19th century, penetrated a huge way down the east side of the Antarctic Peninsula. Now, this was a very considerable feat, because we've analysed the whole range of satellite data for the Western Weddell Sea since the first American spy satellites, now declassified, obtained data in the early 1960s. And there have only been about 2 years over that period, since about 1962-63, where you would have been able to get any significant distance down the Larsen Ice Shelf. So H.C. Larsen's early voyage in the Jason is absolutely an epic. And I think it's great that a number of features down the eastern side of the Antarctic Peninsula are named after H.C. Larsen, his companions, and also the ship that made that epic early journey down the Weddell Sea. And the only comparable year in modern times to that open water, a time in the late 19th century, in the era of satellite imagery, was actually 2002, where it was relatively easy to get a reasonable way down the Larsen Ice Shelf. We in 2019 had a lot of difficulties, not only with obstruction by iceberg A68, but also quite heavy ice conditions. And it turns out, if we look at the next slide, that iceberg A68 helped us out, we think, in a way. You can see where the iceberg was carved from in the image with the Larsen Sea Ice Shelf. You can see where the iceberg came from and where it drifted over a number of months. So it drifted in and rotated in an anti-clockwise direction. And this is about the summer of 2019. We see the iceberg. And because the way the currents flow in the Weddell Sea, and Olaf has already mentioned this, the way there is a clockwise rotation of the water and the ice in the Weddell Sea, that is pushing the berg to the north. But it also means that it's protecting an area to the north of the berg, that dark open water area, from sea ice actually getting in there. And so effectively the iceberg gave our ship a little window to be able to get into the northern part of the area around Larsen Sea Ice Shelf. So the iceberg in a way helped us, but then it rotated further and further around in an anti-clockwise direction. We were there in January and early February 2019, and the iceberg started to come round and close off that whole area. And we actually, at a certain point, had to take the ship out of there. And indeed, some of the tracks that we'd undertaken in January and early February were, a couple of weeks later, actually covered by the motion of that iceberg. And the iceberg, of course, is now moving north. If we look at the next image, actually, we can see...
So before you do that, just one of the things you can see there is that this iceberg must have been grounded on its left-hand side. So it's rotating, being stuck.
Pivot.
Yeah, so you can see it's stuck, and that's why it's not moving very much northwards until it got out of that grounding part, and then the whole thing was afloat, and then suddenly it starts to move much more. But it must have been a bit terrifying for you, Julian, if you had the iceberg starting to close up on you.
Well, we were watching it all the time. You know, the ship's captain and officers were watching it like hawks on the radar, and you could actually see it moving over some of the sediment core sites and some of the oceanographic measurement sites that we'd undertaken in the early part of the expedition. So, you know, we were aware that it was moving. And you're quite right, Olaf, that the reason it's pivoting, and actually the reason there's a little point in the Larsen ice shelf just there is because there is an area of shallows, and it pivoted around that point. The deeper water is offshore, the shallower water is near the Larsen coast, and eventually it managed to break away from that and float further north. But yes, we did have to watch it pretty carefully, and we did have to leave the area because of that in the end.
And if, James, you could put the next slide, I believe that you got quite close.
Yeah, we did. Yes, I think it's fair to say, to my knowledge, we are the only ship that has ever touched the Iceberg A68, and this is the vessel butting up against the edge of Iceberg A68. And if you look carefully to the right, you can actually see just a little bit of the underwater area of the berg as well, which, as I say, extends a couple 500 or 600 feet below the sea surface at that time.
But of course, you're not supposed to do that. You're not supposed to put your ship upright to the iceberg.
Yeah, that's a very good point. That to reassure Viking TV viewers, it takes specialist research vessels and a lot of stability to be close. In times past, I have a feeling that ships were more cavalier about getting very close, and that certainly is extraordinary to be so close. Must have been amazing, Julian, to be close.
It was an interesting experience, and hats off to the South African captain and crew throughout, because we were actually dealing with very difficult sea ice conditions in the Western Weddell Sea. It's of course the area where Shackleton's Endurance was trapped for 10 months and eventually sank in the Western Weddell Sea. And after the scientific part of the expedition, the ship actually went to the site of the last known site of Endurance, and through very difficult sea ice conditions. So the Western Weddell Sea is a very difficult place to operate, and it's only very, very large ice-breaking research vessels that can really do work there.
And if we wind forward to the present day, you were there in early 2019. The next image we have is the latest satellite pass as of date the 1st of December, a few days ago. I can see from this that A68 is travelling north and east across the Scotia Sea and Weddell Sea and across into the Scotia Sea, and heading towards the island of South Georgia.
Yes, you can see South Georgia in this image, which was downloaded by one of my colleagues at the Scott Polar Research Institute just a couple of days ago on December the 1st. And the iceberg is to the bottom left on the image, and you can see it's not that much smaller than when it carved off from the Larsen in July 2017. So some pieces of significant size are breaking off, but it's still a very large piece of floating ice, and it's probably now about 200 and something meters, about 600 feet thick. But above that on the image, you can see in white again the island of South Georgia and various seafloor contours around there, which shows that South Georgia is surrounded by relatively shallow seafloor. And an interesting question is whether or not Iceberg A68, as it floats northward, will actually become grounded on that relatively shallow seafloor that surrounds the island of South Georgia and the other area to the left of the image, which is an area of shallows too. We should bear in mind on this image that it's taken in the it's taken by a satellite, and north is not quite at the top. So the iceberg, rather than being south of South Georgia, is actually to the southwest of South Georgia and about 250 kilometers, about 150 miles offshore at the moment. But it looks to me, and I'd be interested in Olaf's view as well, it looks to me as though there's a significant probability that the iceberg will actually ground on the shallower waters around South Georgia or to its western tip.
Yeah, I think I would agree with that. An iceberg travels, of course, different speeds depending upon the ocean current, but it's typically a sort of 0.1 or 0.2 knots, which, to put that into a more layman term, means that it's traveling maybe 5 miles a day, something like that, a few miles a day, which means that this iceberg would reach the grounded part, reach the shallower waters of South Georgia in roughly a couple of months, maybe a little bit less. And we will know then if it will ground. And then if it grounds, again, it could be grounding like we just saw, the one where it broke off, when it would pivot for a little while and continue, or it might head straight at it and really ground and be stuck there for a very long time. It's going to be very interesting to see, because as you can see in the image, it's almost the same size as South Georgia itself. We're talking about an enormous mass of something. And when it grounds, it is also going to plow up the seabed right at that spot. So if it comes right at it, it will actually get stuck pretty solidly into the land if it hits right on South Georgia. Of course, if it hits just on the outer edge and then pivots around, it may get off again and keep on floating around Antarctica. So there's lots to watch out for here.
And there are examples of what Olav has suggested in terms of the length of time the berg could stay there. From the Ross Sea region of Antarctica, some major tabular icebergs have calved from the Ross Ice Shelf. And when I was in McMurdo Sound earlier this year, in January, February of this year, we saw the remnants of one of those huge icebergs on the western side of McMurdo Sound, some 15 years after it had originally calved from the Ross Ice Shelf. So the melting of a great big grounded iceberg is very slow, and it could take years to decades, to a decade or so, to melt completely. The likelihood, though, Olav, I think I'm right in saying, is that as it melts, it would actually fragment, and therefore bits could ease off and float away.
The melting is we know roughly what the melting is in cold water. So this is fairly cold water. The fragmentation is very much dependent on how stable it is inside also, and what kind of swells it experiences. There could be many things in this, and certainly South Georgia is in a very exposed area. There's a lot of weather passing by here. Yeah. But still, we're breaking through 200 meters or so of ice. It takes a while to make it break up. We shall see.
Yeah, absolutely. And I appreciate that there are, as you say, there are many unknowns. When ice is grounded, I understand that there's a variety of effects on the local environment. There is possibly nutrients that go into the water, which may encourage primary productivity locally. It may affect the weather, possibly. It may affect the access for foraging for the abundant wildlife that lives in South Georgia. What are your reflections on what might be the things that will occur in the near future for South Georgia?
Well, we've talked about ploughing of the seafloor already and the effects on the seafloor biota, but there are good examples, again, from the Ross Sea region, where large tabular icebergs carved from the Ross Ice Shelf have actually impeded the access of penguins to feeding grounds, and their moves from the coastline out to the feeding grounds and back. And that has caused temporary dips in the penguin population in that particular part of the Ross Sea. The penguin population, I think, is largely recovered now, but it did for a few years affect it quite greatly. So that is a possibility. It would completely depend on where and for how long the bird grounded, but that is a possible effect.
But it's perhaps not such a big downside in this case, because the big penguin colonies on the South Georgia are on the east side, and this is going to ground on the west. So, and the amount of food available to penguins is fairly large. I mean, this is the most productive area of the Antarctic Ocean in terms of krill. So most likely, I think we're going to see that the penguins will find their way to get to the food. And unless the iceberg actually stops the access to penguin colony, and they're not really, I think, any big ones, on the west side, if you like, of the South Georgia. It's not going to be that bad. There may be some local effects, like you say, Julian, but I suspect we are not going to see the penguins disappearing from South Georgia. Unfortunately, not.
Not at all, and any effects will be short-lived.
Yeah. And the weather effects in South Georgia of an iceberg is probably not going to be that big. We have glaciers there already, so we are talking about the same temperature. It would be very different if this iceberg was grounded. You would certainly have local weather effects if it was grounded, say, close to the Sahara Desert or something, where the contrast between the snow and ice of the iceberg and the rest of the local climate is huge.
Yeah, so although we think of these tabular icebergs as being absolute monoliths, huge things, their effects are only quite temporary in terms of the environment of the Antarctic and the subantarctic islands.
It is incredible, isn't it? And I feel that maybe there's a nice segue in the comment just made, Olav, that if icebergs were in different places, and may I rather clumsily take us forward to the next point that we'd like to raise with you around whether icebergs can be utilized. We discuss the idea that they are locked up snow, essentially, so it's fresh water. And there are areas of the world with a lack of fresh water. I understand, Olav, that you have been involved in a very ambitious scheme to do with South Africa. I wondered if you'd reflect on that. James, if you could advance the next slide.
Well, about 3 years ago, I got an email from Cape Town, basically asking, "Are you still alive?" This is because 40 years ago, I and several others, including people from Scott Polar and Research Institute, were involved in doing iceberg research. It started with Saudi Arabian prince who wanted to see if he could bring icebergs to help with fresh water in Saudi Arabia. And he established a company which then financed quite a lot of research I was doing in around about 1978, 79, 1980. So it's exactly 40 years ago. And we had the first conference with the results of this actually at Scott Polar Research Institute in April 1980, where a lot of these data were presented. Well, then, for obvious reasons, perhaps, we discovered, and it was easy to find out, that it was not possible to get icebergs across the equator. There was an unsolvable equation, because if you start with such a big iceberg that it would not melt, then it's too big to be able to tow it. So you cannot find a solution to this. But that was across the equator. And so this project stopped. Saudi Arabia stopped looking for icebergs. But then in Cape Town, as we all know, they started running out of water 3 years ago. And they were looking at all sorts of innovative solutions. And then I get this email, and I said, yes, we of course have the results from this. And eventually, I've been twice to Cape Town for meetings on this subject, and we've had about at least 5 meetings in Paris on getting icebergs to Cape Town. And last year, we were at the point where there was investors willing to put up money for this. And the challenge is, and the long-term challenge for Cape Town is, of course, not solved by bringing icebergs. The long-term challenge for them is to get better water reservoirs to handle the water. But it turns out that icebergs is probably cheaper than building a big desalination plant. And there are people who are willing to try that. And this image here illustrates about the amount of water used by Cape Town in 1 year, and the amount that an iceberg would, a single iceberg of about, say, 1,200 feet by 1,800 feet, something of that size, much, much smaller than A68. That would contribute, one iceberg like that, which is towable, it's not so big that it cannot be towed, that would contribute maybe a fifth of the annual consumption of water at Cape Town. And so you could use towing a few icebergs to fill up your reservoirs and bring you back into more normal situation without investing too much more than that. So that's the situation. Now, the realism in this is not obvious. There's a number of challenges. And so I've said, because I don't have money to get into this at that kind of scale, but I've said to investors that if you are doing this, you must be prepared to invest in more than one iceberg, because most likely the challenges of the first tow are going to be so large that you will actually, something will go wrong. Because we're talking about moving something like 100 times bigger than the biggest thing ever moved by humans on the surface of the earth. 100 times bigger than the biggest platform in the North Sea, for example. An iceberg that I showed here is something like 50 million tons. So there's no experience of this. And just thinking of, for example, do you end up in eddies that are moving faster than we can tow, and you get stuck in an eddy and you can't get it out of that, or all sorts of other problems like breakup. How do you do this? But there are a couple of more images showing how to solve, ideas of how to solve it. But it's only when it's practically done that one will find out realism. And this image just shows icebergs observed in this area where you will start towing from. Cape Town would be just out of the right-hand corner of this image, and you see South Georgia down on the south with the arrow on it. And so there are a lot of icebergs that have been seen by satellite in these waters. And we talk about picking up an iceberg maybe at 45 to 50 degrees south, and then traveling eastwards with the current and pulling it northwards into the warmer waters. The colors of this image are the temperature of the water. And in this project is, among the people involved, is perhaps the world's most famous towing captain, Nick Sloan. And he's the one who is behind the third image here. And his concept of doing this is using two huge tankers and two tow tugs to pull an iceberg. And it's illustrated in this image, and there are good reasons why he wants to do it this way. And it was interesting for me to, at one of the meetings in Cape Town, the owners of the world's biggest tugboats came from Holland, from the Netherlands, to this meeting, simply to discuss and see how they could carry this out, because Nick Sloan has a good reputation. He was the one who floated Concordia, the cruise liner that went aground, and done many other projects. So when he says, I'm able to tow an iceberg of this size, he actually has some credibility. Certainly, if I said it, nobody would believe me, but he says he can manage to do it that way. So we will have to see. But the whole thing involves, of course, a lot of money. And as I say, there's a lot of uncertainties. But that's where the project is at the moment. It's not, well, two things have happened. One is, of course, the most important is everything to do with COVID and Corona. But the other thing is, of course, that in Cape Town, people have had to change their behavior. And so the water shortage situation has not improved because of rainfall, although that has improved slightly, but it's improved because they're actually using much less water than they were used to. And if you go to Cape Town today, you don't take a bath in your bathtub any longer, etc., and you don't fill up your swimming pool. But of course, many people would like to get back to a more normal situation, and the farmers have been very, very badly hurt because they've not got enough water for their vineyards or for their orchards, etc. So farming has been hurt very badly in Cape Town. And that you can't cut away, you need the water for that. But in human behavior, that has changed a lot.
I can imagine. And James, if you could advance the next slide, I think we can also see, discussing the feasibility, there's the tow, but the water just to the sort of the southwest of the continent of Africa, around where Cape Town is colder, isn't it? So that once you've got it there, it wouldn't then just melt, I suppose.
No, it would take a while to melt. I mean, an iceberg like this is going to last a year or so sitting there in the water, but both being excavated for the ice. The challenges of getting the water from the iceberg and into the public system is probably just as big and as expensive as towing the iceberg up to this position. And there's another huge challenge related to that part. I asked, how do you expect to do this? But then the authorities in Cape Town say, well, if we actually need the water, we can make emergency solutions to bringing pipelines over land, etc. So they're quite prepared to do something once the iceberg comes there. But the psychology of towing an iceberg is in itself interesting, because the local engineers, the public waters engineers, etc., are very hesitant to putting their, you might say, their credibility into towing an iceberg, because if that goes wrong, they feel that they're going to lose. It's not a proven technology, whereas building a desalination plant, that's a proven technology. So the challenge for those who are the proponents of this project, those who want to invest, etc., is formidable, because they got to get across a mindset of engineers who have never tried something like this and are not really prepared to lose face if something goes wrong. But at the moment, the situation is that those who propose to do this are saying we will deliver the water cheaper than you can make it for desalination. If you're prepared to pay for it, we are prepared to try it. So we shall see. It's interesting.
It's extraordinary. Well, thank you for sharing, Olav. It's I see that as sort of engineering and applied research, and extraordinary. And if it goes ahead, I imagine that will be tracked in the same way A68 is tracked.
Sure.
Day by day. It would be a high profile if it was to go right, or if indeed it was to fall short. And you mentioned about doing research 40 years ago, and I know you have both had illustrious careers in studying ice generally, in glaciology, and specifically on icebergs and sea ice. What would your reflections be on where the direction of research? Julian, you mentioned about the hypersaline areas under ice shelves, and where do you both think that the research is going to go in the coming years?
Yeah, I think glaciology and the perception of glaciology, the study of glaciers and ice sheets, has really changed over the last half century or so, from being regarded as something that was interesting but a little bit quirky and not very relevant to the world at large, to really all glaciology being applied glaciology today. That is to say, that the changes that go on in the Arctic and the Antarctic concerning, for example, glaciers and ice sheets, are a fundamental control on the amount of sea level rise that we will have to deal with worldwide over the next 50 to 100 years. And one of the big aims of glaciology today is to predict how much melting, how much mass loss will take place from glaciers and ice sheets over that time period. Will global sea level rise by 80 centimetres, or by a metre, by 3 feet over the coming, by 2021, or will it be more than that? And one of the things that we really need to know about, with that in mind, is the nature of the way that ice flows over its bed. It's very difficult to look at that, because the bed of an ice sheet today is covered by up to 3 or 4 kilometres, a few miles of ice. And we can drill through and put instruments down there. We can use geophysical methods to try and see what the water content of the sediments that underlie the ice are. But we really need to improve our knowledge of that interface, that boundary between the ice and the sometimes lubricated bed on which it sits, in order to try and model numerically by computers the way that ice sheets may respond to one of a series of possible climate futures. And of course, those climate futures themselves will depend on how humankind responds to the present initiatives to cut greenhouse gas emissions.
Well, thank you, Julian. And Olav, do you have reflections also?
Well, I think Julian has mentioned the important things, that the interaction of ice and glaciers with our living conditions today, we are much more aware of that than we were back when glaciology was purely academic subject. Now it is relevant to climate change, it is relevant to sea level change, and we will see that even more so, I think, in the research of our subject in the coming years. Frankly, whether icebergs get towed or not is a minor detail in this rather big question. But should that become a relevant thing, then of course we will see some very specialized iceberg research simply to make that more feasible. So we shall see. That's also a matter of climate change, what's happening to fresh water. There are other places on Earth which, if one ever managed to tow icebergs to Cape Town, which is the ideal position, the next step could be to tow icebergs, say, to Namibia, which does not have any rainwater to any extent. So there's future in that if it should ever happen. We shall see.
Fantastic. Yeah, and having asked you about the future, may I ask you to reflect on your careers a little? I can only imagine that the myriad experiences that you've had interacting with ice, and from the images that Julian showed from his being lifted onto icebergs from when at the beginning of our conversation. Do you, of the many experiences you have, may you both maybe share one thought, Olav, if you had a reflection of a particular experience?
Over the years, of course, there have been many experiences, but when it comes to just with icebergs, the one happening that caused most news media coverage in my whole career, perhaps, was in 1981. We were down with the HMS Endurance on a joint project between Scott Polar Research Institute and the Norwegian Polar Research Institute. And we happened to be on the same ship together with David Attenborough's film team. And they, of course, were down there to do a story within this, Life on Earth series of one kind or another. But they got interested, of course, in the research we were doing on the icebergs. And so on one of the trips when we were putting up stations on the iceberg, flying out with helicopter, they asked if they could come along to film this also. And which they did, and while we were there working, fog got stuck there, and then the helicopter could not come back to pick us up. So after a few hours, we realized we would have to spend overnight on the iceberg. We fortunately, because you always do, had with us a couple of tents, and we had with us some food. So we were happy, and we knew next day at some point the fog will lift and we will be taken off the iceberg. And this was a big tabular iceberg, not the A68, but it was more than half a mile across. There was no way it was going to break up or roll over or whatever. And in my career, I've landed on something like 30 icebergs and spent hours on them. So I was very comfortable. David Attenborough was very comfortable. But back in London, apparently the news got out that David Attenborough was stuck on an iceberg and was about to die. And of course, he was interesting in a way that we never would become. And the news and the media stories that were formed on this particular happening were apparently enormous. But we knew nothing about that until we got back onto the ship. But it was fun to be with people like that.
And I imagine, spending a night on an iceberg is unusual.
It is very unusual, I can say that. And I think he enjoyed it very much. And many years later, I had a project in Norway, which I wanted his voice to take part in. And I said, we had also some British people involved. And I said, well, let's get David Attenborough to give the voice to this. And they said, no way, he doesn't do any work outside BBC, etc. And I said, I'll just write him a letter. I didn't tell them I had met him before and that we actually got to know each other very well. I just said, I'll write him a letter. This project is so good, I'm sure he will say yes. And which, of course, he did. He said, I'd be delighted to do this. Yeah. And they couldn't believe it. And this is the first time I ever say this publicly. So if they ever hear this, they will now get the explanation why he came across and did the work. It's because we spent the night on an iceberg.
Oh, I imagine it's very bonding. Well, thank you for sharing that, Olav. Julian, have you got a particular memory that jumps out in your career?
Yeah, yes. I mean, not all of them for public consumption, I think. But no, the polar regions have been a fantastic place, and I'm sure Olaf would agree, to go to on a very privileged regular basis over on the timescale of a number of decades, both the Arctic and the Antarctic. We saw earlier one of those beautiful images of the iceberg keel ploughed sea floor, and that's an aesthetic, of course, that we don't usually get to see. But as director of Scott Polar, I'm lucky enough to have a very fine painting in my office, which is called The First Iceberg. And I remember when I first went to Antarctica, and firstly, the water and the air starts to get colder, and then you start to look out through the binoculars on deck for that first iceberg, because the icebergs have got a higher freeboard, so you see them generally before you see the sea ice, certainly coming down the west side of the Antarctic Peninsula. And I remember the excitement of actually, and it was just after dawn as well, of looking through the binoculars from the bridge of the ship and finally seeing that first iceberg that I had imagined for much of my life before I went to Antarctica. And it was a super exciting moment to see first that iceberg, and then to go past it, then to come into the sea ice, and then to see the mountain peaks of the Antarctic Peninsula after that. And that's something I certainly will never forget. But more generally, I think the aesthetics of the polar regions, the wildness, the quiet and the beauty are just absolutely fantastic. And I'm sure Olaf again would agree that it's been a privilege to work in places like that over the past decades. Very lucky.
Oh, no, thank you for sharing that reflection also, Julian. And just to wrap up our conversation with our viewers, many of whom who hopefully will be inspired by this conversation and others to go and explore polar regions for the first time. What would your advice be in how to observe icebergs? And what any tips you might share with those that have not yet had that first experience that Julian's describing and that you both have witnessed?
Yeah, I think firstly, a good pair of binoculars is really something that's enormously valuable. It's no coincidence that there are, binoculars scattered around the bridges of ships, and I think that that's really a very big thing. A decent pair, everybody's going to have a camera, but a decent pair of binoculars is really a good thing. And also, because it's cold, whether you're photographing seabirds or whether you're looking for icebergs, you're going to be outside. So I think having gloves that still keep you warm but allow you to manipulate a camera is quite a big thing as well. So those sort of little details can make some of the difference between really getting some great photos and having constantly irritatingly frozen fingers. So just a small point, but perhaps useful.
Oh no, thank you, Julian. And Olaf, have you any?
Well, you asked about icebergs. Look at the structure of the iceberg. When you see it first time from a distance, it looks like one piece, white piece. But if you look at it closer and get close to it, and the ships will be close because it's quite safe to get close to an iceberg. They're very deep. You don't go aground or anything. You will often see interesting structures. We talked about the tilting you're seeing for previous waterlines. Julian, I think, mentioned that you've got the annual layers of the structure and horizontal structure in them, but you can also see all sorts of wave cutting features. Some places you will see deep hollows going into the ice, etc. So they're often interesting. And then you will see the blue color. And the blue color we haven't talked about, but the ice itself, of course, is blue because that is the color of ice, very faintly blue. And you can see if you see into the iceberg, where you had waves cutting hollows into the iceberg, you will see blue, very nice blue colors, and that can be fabulous. And sometimes you see small growlers maybe you out in a small boat and you are close to a growler, also you can see some very fabulous blue colors in these things. And that's always fascinating.
Yeah, I think the colours are an interesting thing. I mean, at the Scott Polar Research Institute, we hold hundreds of beautiful watercolour paintings by Edward Wilson, who was on Scott's 2 expeditions. Absolutely beautiful. And again, if you think of what probably the first professional painter, one of the first professional painters to go to Antarctica, Edward Seago, who went down in the 56, 57 to Antarctica, his comment was, I expected it all just to be white and grey. And actually, there were a myriad of colours. And I think that's something that everybody will really enjoy. And in a way, it's a little unexpected.
Fantastic. And James, just if you wouldn't mind sharing, there's an image of an iceberg with the ship shadow, which I think maybe illustrates Olav's and Julian's points about the colour, proximity to a vessel. And to me, that very much resonates with my first sightings of icebergs at the early part of my career also. But a very lovely image to hold as we complete the conversation. I'd now like to, first of all, thank both of you very much for taking the time to share your insights about icebergs, about what they are, and indeed how relevant they are to a broader understanding of global conservation and global processes. So thank you, Olaf. Thank you, Julian.
Good, Damon.
And may I also thank you, Viking.TV viewers. Thank you for taking the time to indulge us as we talk about the wonderful world of icebergs. And until next time, thank you.